Let's take the next 20 minutes to talk about intersection sight distance and gap acceptance and to work through two example problems from the text. We begin by recognizing that an at-grade intersection experiences a variety of conflicting movements as vehicles and bikes on each approach move left, through, and right, and pedestrians move from one corner to the next. Users must be able to see each other in time to assess whether an impending hazard is imposed, and with time to stop or yield as necessary to avoid collision. Where it is not reasonable for users to perceive and avoid conflict, traffic controls are installed to restrict and assist. The controls are selected and placed to manage the various movements in a manner that promotes safe and efficient travel for all users. In this exhibit of vehicle-to-vehicle conflicts, we find 16 potential crossing conflicts, plus 8 merging conflicts, and 8 decision points for diverging. Upon further examination, we find an additional 24 points of potential vehicle-to-pedestrian conflict. The selection of an appropriate level of intersection control involves identification of conflicts that a user should be able to perceive and avoid through the exercise of judgment. When it is not reasonable to expect a user to perceive and avoid a particular conflict, traffic controls are installed. 3 basic levels of control can be implemented at an intersection. Level 1 control is where the basic rules of the road apply and there is no explicit assignment of right-of-way. There are no signals, no stop signs, no yield signs. Level 2 control is direct assignment of right-of-way using yield or stop signs. Level 3 control is traffic signalization. Determination of an appropriate form of intersection control involves considerations of sight distance, assessment of demand intensity, and the analysis of available gaps in the major stream. Let's begin by taking a look at intersection sight distance. Sight distances must be analyzed to ensure enough sight for users to judge and avoid conflicts. Sight lines can easily be obstructed by buildings or other features located on or near the corner, and by curves in the geometry of the road. This figure illustrates a visibility triangle at a typical intersection. At the point where the drivers of both vehicles first see each other, Vehicle A is located at a distance dA from the collision point, and Vehicle B is located at a distance dB. The sight triangle must be sufficiently large to ensure that vehicles on conflicting paths have sufficient time and distance to avoid collision. The triangle is dynamic in that the position of one vehicle affects the position of the other when visibility is achieved. Notice that the sight line forms 3 similar triangles. At the upper right, we find triangle 1, 2, 3. The full triangle is 1, 7, 4. At the lower left, we have 6, 5, 4. According to the properties of similar triangles, we find that segment B is to segment DB minus A as segment DA minus B is to segment A. Rearrange the equation and solve here for dB, which is the distance from vehicle B to the collision point at the moment mutual visibility is first established. It would be a shame if dB were less than the distance needed for vehicle B to perceive the hazard, react, and decelerate to a stop. The properties of the visibility triangle have application for level 1 control and beyond. Let's begin with level 1 control, where vehicles operate under the basic rules of the road. The basic rules of the road apply at any intersection where right-of-way is not explicitly assigned by use of signals or stop signs or yield signs. The right-of-way rules are spelled out in each state's vehicle and traffic law. Before permitting this type of control, the sight distances must be analyzed to ensure they are sufficient for drivers to judge and avoid conflict. It is necessary that dA be at least as great as A's stopping distance, and that dB be at least as great as B's stopping distance. This recommendation comes from AASHTO, the American Association of State Highway and Transportation Officials. Here we recall that stopping distance is the sum of reaction distance plus braking distance, and that certain assumptions are made regarding operating speed, reaction time, deceleration rate, and/or friction factor. The following 4 steps may be used to test whether an intersection sight triangle meets AASHTO's sight distance requirements. Step 1. Assume A's actual location is one safe stopping distance from the collision point, such that dA actual is equal to dA stop. Step 2. Use the visibility triangle to compute the actual position of B when first visible to A. The current Step 2 features the computation based on the properties of similar triangles. Here we find that dB depends on dA, which is set equal to dA stop, and depends on A, which is driver A's position relative to the sight obstruction, and also on B, which is driver B's position relative to the sight obstruction. Step 3 is to compute B's stopping distance, dB stop, which is to be taken as B's minimum acceptable distance. Step 4 is to compare dB values and ask, is dB actual at least as long as dB minimum? If the actual distance for B is not at least as great as that needed for B to bring the vehicle to a stop, then the sight triangle is too small. Let's see how the steps work in the context of the example problem, where A's speed is 30 miles per hour and the A driver is 20 feet from the obstruction, where B's speed is 40 miles per hour and the B driver is 42 feet from the obstruction. Step 1. Assume A is one safe stopping distance from the collision point. A's stopping distance is computed here to be equal to 196.5 feet. That means that during the time it takes to perceive, react, and decelerate to 0, A travels that distance. Step 2. Use the visibility triangle to compute the actual position of B when first visible to A. dB actual is computed here to be 25.4 feet. That means that with A 196.5 feet from the collision point, B doesn't come into view until B is 25.4 feet away. Step 3. Compute B's stopping distance. B's stopping distance is computed here to be equal to 300.3 feet. If we take dB stop to be the minimum acceptable separation between vehicle B and the collision point, then dB minimum is 300.3 feet. Step 4. Compare dB actual to dB minimum and find that the actual separation, 25.4 feet, is less than the minimum acceptable separation, 300.3 feet, and tend toward concluding that this is an unsafe condition. What do you think? If A is a full 196.5 feet away, when B is only 25.4 feet away, it would be unlikely that these two vehicles would collide. Yes? Consider, however, that there could be unseen vehicles on a collision path with A that are further than 25.4 feet away. In this case, the drivers would not be able to see each other. Thus, the traffic engineer would likely consider imposing stop control on the minor street. Here we find that the MUTCD warrants for stop signs identify three conditions for considering stop sign use. Condition A is where vehicle volumes on the major street exceed 6,000 vehicles per day. Condition B points to sight distance restrictions causing minor street drivers to stop in order to adequately observe conflicting traffic. Condition C is 3 or more correctable collisions within 12 months or 5 or more correctable collisions within 2 years. So we find that Condition A prescribes a level of major street traffic that would require use of a stop sign in order to allow minor street drivers to select an appropriate gap in a busy stream. We'll be talking more about gap acceptance in a moment. Condition B restates the need for control wherever sight triangles are too small to perceive and respond to hazards. We've already taken a look at that. Condition C establishes criteria for correcting an apparent accident problem due to failure to yield right-of-way. We must also be aware of MUTCD statements regarding inappropriate uses of stop signs. The MUTCD says that stop signs shall not be co-located with signals. This disallows a past practice of turning off signals at night, leaving stop signs in place for the evening hours. The MUTCD also states that stop signs should not be used for speed control, although this is frequently done on local streets when arranged in an open grid pattern. While a sight distance problem can be corrected by imposing stop control on the minor street, that does not necessarily mean that two-way stop control is sufficient for correcting sight distance problems. Let's take a look at the sight distance criteria for stop-controlled intersections and another application of the visibility triangle. This methodology is based on gap acceptance. Gaps in the major stream are opportunities for minor street vehicles to cross or merge. Here's a useful definition of gap. The gap is measured in seconds as the time lag between two successive major street vehicles encroaching on the minor vehicle's crossing path. To be acceptable, the gap must be large enough for the minor street vehicle to safely cross or merge. At a two-way stop-controlled intersection, we might ask a question such as this. What if the driver requires an 8-second gap, but conditions are such that the encroaching vehicle is only 6 seconds away when it first comes into view? This creates a potentially hazardous condition where the visibility triangle is too small to accommodate the gap acceptance behavior. The following steps can be used to test whether an intersection sight triangle meets the sight distance requirements for gap acceptance. Step 1. Specify the location of the driver of the stopped vehicle relative to the point of collision. This can be taken as the sum of 3 distances: the distance between the driver's eye and the front of the vehicle, the distance between the front of the vehicle and the front of the curb line, and the distance between the curb line and the collision point. Step 2 is to compute D minimum as a function of the size gap that A will accept. Step 3 is to use the visibility triangle to compute dB actual to represent the actual position of B when first visible to A. Step 4 is as before. Compare dB values and ask, is dB actual at least as long as dB minimum? If not, there is insufficient sight distance to meet the gap acceptance criteria. Let's see how these steps work in the context of the example problem where A is stopped 36 feet from the point of collision and requires a 7.5 second gap, and where B is approaching from the right at a speed of 40 miles per hour. Step 1. Specify the location of A relative to the collision point. With the assumed values given here, dA is computed as 8 plus 10 plus 18 equals 36 feet. This is driver A's I distance from the point of collision. Step 2. Compute dB minimum as a function of A's 7.5 second acceptable gap and B's 40 mile per hour speed. We find that 1.47 times 40 gives speed in feet per second, and we multiply by the 7.5 second gap requirement, solving for dB minimum equal to 441 feet. This means that when vehicle B is 441 feet or further, the gap is acceptable for the movement A intends to make. Step 3. Use the visibility triangle to compute the actual position of B when first visible to A. dB actual is computed here to be 576 feet. This means that with A 36 feet from the collision point, B doesn't come into view until B is 576 feet from collision. In step 4, we compare dB actual to dB minimum and find that the actual separation of 576 feet is greater than the minimum acceptable separation of 441 feet. We conclude that for vehicles approaching from the right, the sight distance criteria are satisfied. The textbook example also evaluates sight distance criteria for vehicles approaching from the left and concludes that there is not sufficient sight distance to meet the criteria. Options include removing the obstruction, cutting back the obstruction, calming the approach speed, or shifting A's stop position forward. So far, we've talked about gap acceptance for drivers. What about pedestrians? Do pedestrians evaluate available gaps to accept or reject when preparing to cross at unsignalized locations? We find a brief discussion of pedestrian gap acceptance in Chapter 2 of the text. On this slide, we find additional comments pertaining to the courtesy phenomenon, in which major street vehicles may voluntarily yield right-of-way to pedestrians as pedestrians prepare to cross the path of the vehicle. We also find a list of factors to consider to properly assess pedestrian gap acceptance, including walking speed, trip purpose, and risk-taking. We begin to understand that gap acceptance behavior is quite complex and varies with a number of factors, including those just mentioned, plus approach speed, the geometry of the intersection, the intended maneuver, how long a user's been waiting, and others. We also find that gap acceptance behavior, as well as gap frequency and distribution, are important considerations that must be properly accounted due to the safety and operational implications. In closing, let's recognize that gap data is used to determine the number of opportunities for a user to execute a pedestrian crossing, a turning movement from a stop-controlled intersection, entry into a roundabout, a permitted left turn at a signalized intersection, and right turns on red. The gap data is applied in capacity analysis for improving safety and level of service. This website provides information on a product sold to measure gaps and report gap data. There are more rudimentary means of data collection that can be applied for a focused study of gap acceptance. We anticipate giving our attention to gap data analysis in a future activity.